Thank you everyone for joining. Really happy to have everyone here. This is the first of a series of introductory webinars that we'll be doing here at Satora. We also have some more advanced webinars after this one that you can join in if you want to learn more about any of the topics that we're discussing here today. So first of all, my name is David. I'm head of marketing at Certora. Who is this workshop for? This is for developers, especially if you're just starting to learn about formal verification, or if you are already familiar, but you are just looking to get more familiar with our specific tools and implementations. This is also something that if you're working with our tools and you're starting to get the hold of it, you can share with your teammates and send them here as well to get them started on this journey with our tools that can be, as you'll see in this workshop, quite powerful for helping you secure your code. So without further ado, the structure of today's webinar is going to be a quick intro by our CEO, Muli, who will give a more of a framework and some details of how we approach formal verification and how we fit into the overall security landscape. And then we'll have a very practical live demo showing you how to get up to speed with everything that you need with the Certora Prover, and then the next steps that you can take. And be sure to stick around to the end. We have some special announcements. We may also have some keys, some demo keys for people to get started using Prover. So we'll have those announcements after Mike's demo. Muli's introduction is going to be around 10 minutes, and then we'll have around 40 minutes of the actual live demo. So take it away, Muli.
Thank you very much. Thank you, Mike. Thank you, David. Let me try to share. Can you see my slide, everybody? By the way, if you have questions, just put it in the text and we will respond. So I'm excited to be here. I've been actually a veteran in this field of formal verification. And Satora is trying to get this formal verification into a real thing in DeFi. The technology is actually rather general, but we are really focusing on DeFi at the moment. We are actually enthusiastic in this field. Many of us may have many years of experience. Basically, this is a mature field of computer science. The idea is you have a program and you want to make sure that the program does what it's supposed to do, or actually find a deviation between what the program and the requirements. And also we team together with the expert in DeFi. So these are security researcher, people who are interested in finding the security of DeFi, and we team together to help secure the protocols. So the master DeFi is very interesting for many, many reasons, but one reason that it's interesting, at least for formal verification, is that the effect of bugs is really, really high in terms of the loss, the potential loss, and it's really hard to recover them. So, and some of them, for example, the case of the oiler, a very, very little change in the code resulted in a huge loss. And these bugs happen and again and again and again, and technologies like formal verification, they're trying to prevent these bugs. And the idea is to try to think about it like an exhaustive testing, that you want to avoid these kind of bugs, and you want to avoid bugs at the beginning of the code, and you also want to avoid bugs when you change the code. And this is the technology that Satora is developing. So maybe just summarize why do we want to formally verify code? So basically, we think of basically DeFi as almost like a safety critical code, in a sense that really the code is law. So basically, if you have a wrong code, you have a wrong law that somebody can exploit. And there's a lot of money at stake. From a formal verification is really a technique which is usually hard to scale. So therefore, from a technology point of view, it's an interesting domain for formal verification because the code is typically small or modular. It's not like you have a huge spaghetti code, but still it's very, very interesting because traditional testing is very hard to find some of these bugs. We are talking about event-driven program. We are talking about programs that the one behavior is depending on another behavior. They are calling each other. And this is what makes formal verification more interesting in this domain. And perhaps the last but not the least, that the code is frequently changed. the business and the fact that you have bug, it's really cause people to write new and new code. And formal verification in the DeFi, I think it's one of the interesting domains that people have tried to use formal verification outside hardware. So one team, which is called Maker, which is one of the most interesting teams, which is basically building a stable coin, they use the formal verification. They actually use the Certora Prover, and they write rules all the time. And they use the rules to prevent bugs and to find bugs. They usually work with the top auditor, so usually they will run the prover, and after that they will approach the auditor to find if there are bugs. And what they are finding is that actually the tool is very, very good in finding bugs before and after the audit. For example, they recently actually found a mistake with the prover that actually allow you to break the stability of the coin. So this could have lost in billions of dollars mistakes. So that's one team who's using Maker. And recent team actually, Lido. Lido is one of the most interesting protocols for staking in this space. They have now re-implemented the withdraw function, and they use the Satora team to actually write rules. And actually, this is published in our Twitter today. Is basically you have a report of these are all the bugs that were found by formal verification. So Satora is actually building a tool. And you can think of a tool as a formal verification, but you can think about more as a traditional security tool. And here we are pointing out several methods to do security. So one of the most useful one is using testing and fuzzing. You want to try your program as many as input as possible. This is very useful. The techniques like the American fuzzy loop is actually being used in all software to find mind-blowing bugs. That's very interesting. In the blockchain, there's Echidna, and by 12-bit, and there is Forge by Paradigm. So these are all tools that are doing random testing and becoming standard in these methods because they're really, really able to find many bugs. But unfortunately, it's hard for them to find bugs which include many, many dependent behavior. The other method is static analysis, also actually widely developed in Web 2. And there are tools like Coverity, Veracode, Checkmark. So all of these tools, they check your code before it's deployed like a compiler. And it actually gives you some behavior. Actually, Certora implements certain static analysis. The problem with static analysis, so testing has these bugs which are hard to find. The static analysis, it has false positive and false negative. So what Certora is doing this method which is called automatic formal verification. You compile your code into a mathematical formula. This is an old idea which is done in many, many methods. Particularly, I pointed out the Daphne, which is a huge effort by the Microsoft research, but there are other tools. And these are open source tools for checking the code. Usually, you don't do it on a normal programming language. You design your own programming language. Certora is actually developing a huge effort to scale these kind of techniques for much more complex programs. So this is effectively a bug finding. You can think about it like fuzzing, but unlike fuzzing, you do not start in an initial state. You start in an arbitrary state, which is defined by the programmer. So this gives you more coverage, but makes the search problem for searching for bugs harder. And this is where Satora innovates. We try to develop algorithms which make this technique more scalable. And the last technique is called proof assistant. This is actually done like companies like runtime verification. You use a system that actually derives the code from the spec. For example, the runtime verification was able to go from a case specification into virtual machine. So you can get a virtual machine which is stronger. We are not interested in proving the virtual machine. We are more interested in checking the individual contracts. So just to show you this pictorially, so basically you see testing and fuzzing. These are techniques that are able to find many bugs. Certora Prover is covering more bugs because once you have a specification, we can show you that you will exhaustively find all the bugs in the specification. The static analysis, it's complementary. It's of course very useful, but it can sometimes miss bugs, and it can also find bugs which are not real. So maybe we can think about it as two scale, how automatic it is and how secure it is. So tools like K, Cork, Daphne, Isabel, and Lean, people use it to build a lot of secure code. For example, people have used code to prove the correctness of a C compiler. People have used Isabel to prove the correctness of operating system. These are huge effort. Usually we are talking about 20, 30 years of human that you are proving, usually something like 300 lines of code. Okay, so this is a very, very interesting domain, but it's very hard to scale. And the other extreme, this is fuzzing. It's something that every programmer can use, and it's actually identify some bugs. So Satora, we are trying to find something in the middle, something which is perhaps not as expressive, but nearly as expressive as Coq, but also make it easy to use, almost like fuzzy. And we decide actually not to verify the source code. We decide to verify the executable code, which makes our problem harder, but we are able to show that the actual executed code is correct, and we are also able to find bugs in the compiler itself. We're also trying to make the spec easier to use and to use modularity in a way that the programmer controls. So we are not dictating any kind of a programming style. You can actually verify program with arbitrary style. So what do? We have this language CVL that Mike will able to explain to you. So this language is language for writing invariant, for writing properties of your code. It's not an executable language, although it's basically a declarative language. It shows you some properties of your code. And then we compare the executable code to the specification in order to prove bugs, and in order to to find bugs and prove their absence. So how does it work? It actually can check properties, but the interesting thing about technology that you can integrate it into your CI, and every time you change your code, you can check that it has the property. And Mike will be able to show you these kind of things in detail, but the idea is this is something in addition to fuzzing and other things that you integrate into your build cycle to make your software more secure. So one question that we always ask, especially in this domain where you have a lot of money, does this technology replace auditing? And the answer that we say no. This is the case that the human and the computer are actually complement each other. So the idea is you write your DApp, you write your DApp, you write your smart contract, you design it, you write the code, you want to do the audit. But in addition to that, you want to write the requirement, and you want to write the requirement as early as possible. And you can write the requirement on the design, you can write the requirement on the code, and then you check the requirement hold, and we have a technology called Gambit that will be that basically can check the requirement, and we also basically check that the program adheres to the requirement. And this is something which is done by the Certora Prover, and eventually everything has to be done to an audit. So the auditor can look into the code, it can also look into the spec. And the auditor can find bugs in the spec, and usually the tool actually can find bugs in the fact that the specs is not violated. And Satora actually found bugs before audit, after audit, because the more the spec, you make your code more secure. And the earlier, the better. And you can use this technology to secure your code and make the executable safe. So I'm finishing my introduction. Let me just tell you few of because formal verification, as I said, it's a mature field of computer science. There are many actually Turing Award in this domain, probably more than other domain. It's a complex domain, and many people have done fantastic job. So one thing which is interesting about formal verification, that the natural thing is that you think about it as finding a proof. And of course, it is finding a proof. But the most interesting application, and this is already observed in the hardware industry, is that the formal verification can find bugs for you which are surprising. So it can prevent these bugs. You can think about it like a QA, but a QA which is very exhaustive. The other thing which is very interesting about formal verification, this is one of the hardest computational problems in computer science, which range from NP-complete to undecidable, which means that the computer can never really prove your property. But in fact, we see that the hardest problem, Certora and many other companies that try to implement formal verification, is getting people to write specification. And we can point out that the teams like Maker, Syndicate, many other teams in the DeFi that writing their own specification, they are doing already something which is interesting. But perhaps another misconception about formal verification that people think that they verified the code and they don't need to test it. And there is a very famous quote by Knus, who's one of the giant computer science, that I don't trust this code because I only formally verify that. The idea is that formal verification is not actually a replacement for testing or for any other method. And you want to do as many things that you can do, and maybe either do monitoring or do anything that you can do to protect your code. I already pointed out that formal verification is actually complementary to auditing. And the last thing that maybe a thing to do is formal verification comes early. And you want to shift security left, and you want to start formal verification as early as possible. So just the last slide, I want to point out to you, and I'm sure you know, bug finding is a very hard problem. Auditing is great. People are finding a lot of bugs after auditing, even by the top auditors. And there is, of course, crowdsourcing auditing, which is very interesting, but even crowdsourcing is not perfect. Fuzzing is great, but it usually starts from initial state. And sometimes it's hard for the fuzzing to find deep bugs that happen after many situations occur together. And these are, for example, leads to solvency and many tricky issues. So what Certora is doing, and probably it will be explained to you if you attend the more advanced webinar, it combined two techniques in computer science. One is called SMT, which is mathematical constraint solving, and the other is called static analysis and abstract interpretation. And these are both techniques which are hard, but they actually simplify each other. So the SMT simplifies the static analysis, and static analysis simplifies the SMT. So by solving these two hard problems together, you actually get something which is better than each one of them. And as a result, we get the tool, which is, you can think about it like automatic formal verification or exhaustive testing, and it can start from an arbitrary state and find tricky errors. And Satora is taking an approach. There are other teams who are trying to dictate some kind of programming style. We basically verify what you write, and in particular, we verify the executable code. So I'm happy to take question, or I think I can transfer to Mike George, who will go to the technical part. David, what do you think is the best?
Thanks so much, Muli. I think given the time, let's dive right into Mike, and then we'll take the question at the end if there are any that come up. Thank you so much, Muli, and we will dive right into this. I'm really excited for what Mike has to offer here. You'll see that we are we'll start really basic, and by the end, I promise you, you're going to have your mind blown by what this tool has to offer. So without further ado, here is Mike.
Thanks, David, and thanks, Muli. My name's Michael George. I'm have many hats at Certora. One of them is head of education, so that's probably the hat I'm wearing now. And I want to show you, get our hands a little wet and do a demo of the prover and show you how to write specifications. I'm going to start with kind of a toy example. This is a little bit of a constructed example, but I think I want to use it to show you how the interface to Certora works and how it's different from something like testing or fuzzing. So let's say we have this contract. I've called it example. Like I said, it's a contrived example. And there's this interesting function f, takes in an integer x and returns another integer. And it's defined by this formula, right? It returns 4x squared plus ax minus 3a squared, right? And the claim by the developer, the important property that they care about, again in this contrived example, is that this function should never return 0. So let's think about how you would actually write a test for this. And we'll also show you how to fuzz it and how Certora would approach this. So let's say we wanted to write some tests. Well, how would you do it? Well, you'd set up your example contract, create a contract, and then you'd call the function a bunch of times, excuse me, and you'd assert that the result of the function call is not 0. And you'd try a couple different inputs. You might try some edge cases. You might throw in max uint or something. I don't know, you might try a, right? Because that looks like an interesting constant. So you would try a couple different things, and then you run it through your test framework. It'll run this code. None of the assertions fail, so all the tests pass, and it'll give you a thumbs up. And in fact, it has executed all of the code paths in the program, so it'll say, you have 100% coverage, and all your tests pass. Great. Now, that's only testing a couple of cases. So A more interesting technology is fuzzing. So with a fuzzer, if you're familiar with a fuzzer, you write a function, and the idea is that the fuzzer is going to call that function with a lot of random inputs. So instead of just these 3 randomly chosen inputs, the fuzzer is going to execute, for 10,000 iterations or 100,000 iterations, or run for a couple days. And what it'll do is it'll keep generating random numbers and calling the test. And then this test generalizes these tests up here. It takes whatever that value x is and runs the f of x and checks that it's not 0. Okay, so you run your fuzzer, for a long time. Again, you'll get a 100% coverage, and you keep running, you won't get any violation, and so the fuzzer will say, this looks good to me, after you get bored of trying counterexamples. Let me compare that to how Certora would do it. So in Certora, the interface looks actually very similar to how you would write fuzzing tests, right? Here I've moved the int x down out of the arguments, and I've written the word rule instead of function. But it's basically the same thing. We take an integer x, we take an integer x, we plug it into f and compare it to 0, and the goal is that this should never be false. Okay. There's one thing to notice here before I show you how the prover processes this rule. One difference is, with fuzzing, you have to set up the state of the system ahead of time. You have to say, I'm setting up the contract by calling this constructor with the value 3 so that the value a is 3. With Certora, you don't have to do any of that setup, and I'll show you why. So Certora will see a rule like this that you've written, and here's how it will try to find bugs using that rule. So instead of just giving it random inputs, it's going to do some reasoning. So it's going to say, your assertion is f of x is not 0. Okay, well that assertion would fail if f of x was 0. Well, we can look at the code. F of x would be 0 if this expression is 0. So let's try and figure out, can we make that expression 0? Well, that's a quadratic equation, and we all learned in, I don't know, high school or something, how to solve quadratic equations. So we can factor the equation, and we get 4x minus 3a times x plus a, right, is equal to that. So this complex thing is 0, if and only if this simpler thing is 0. And to make that 0, you can make the first thing 0. So this would happen if 4 times, sorry about that. This would happen if 4 times x was the same as 3 times a. And can we solve that equation? Yes, we can. Let's pick 3 for x and 4 for a. If we do that, then this equation holds, which means this equation holds, which means this equation holds, which means f of x is 0, which means, hey, your assertion over here is false. Okay? So the prover would actually be able to find this example. Say, if you start with x being 3 and a being 4, then your assertion will be violated. And so Certora will be able to find this rare bug that these other techniques would not be able to find unless you got very lucky. And in fact, neither of these would ever find it, because it's impossible to solve this with a equals 3. But that's not the point. The point is, with testing or with fuzzing, you have to get very lucky to find a hard to find bug. With Certora, because it's trying to construct a proof, it will either find exactly the case or exactly a case where your assertion is violated, or it will produce a proof that says it is impossible to violate this assertion. So that's what separates Certora from other techniques. But the way you think about writing Certora rules is the same way you would think about writing fuzzing tests in particular. Okay. So this is kind of a toy example, but I now want to go to a slightly more realistic demo to show you how I would use it in a DeFi application. So I'm going to focus on the ERC20 spec. I'm hoping that listeners are familiar with ERC20. This is a standard token interface, and I'm going to focus on these 4 methods. So there's a transfer from method, which should transfer a certain amount of tokens from whoever's holding them to the recipient. There's a balance of that lets you see what the balance of a given account is. Now, transfer from, of course, you shouldn't be allowed to transfer anybody's tokens to anybody else. You need to have an allowance in order to do that, and this function allowance tells you what, how many tokens spender is allowed to spend on behalf of the holder. And then that allowance you need to be able to set, and so there's this approve method. You can call approve to give somebody else an allowance. So that's how an ERC20 token works. The very short version, but again, I'm assuming you are familiar with this. So what I want to do now, I'm going to switch over to my editor, and we're going to write some specs that take a look. We're going to start with transfer from and see if we can prove various properties about the transfer from method. So let me switch over to my editor here. I'm showing you here, I'm using my favorite text editor because I've been using it for, I don't know, 20 years and I'm used to it. We actually do have a nice VS Code extension, and I encourage you to check that out. But I'm just going to use a vanilla text editor here. So on the left here, I have the ERC20 interface. This is Solidity code. On the right, I'm going to write a specification in our verification language, which we call CVL. Okay. And I wanted to focus on the transfer from method. So let's take a look at that. Okay. And so I'm going to write a rule, and that rule is going to describe how the transfer from method is supposed to behave. Okay. So the way you do this is you write rule, and then you give it a name. I'm going to call it transfer from spec because it's the specification for the transfer from method. Okay. And the thing I want to check is that transfer from should, well, what does it do? It moves amount of tokens from sender to recipient. So I'm just going to first write a specification that it says it should reduce the sender's balance by amount and increase the recipient's balance by amount. Now, if I wanted to write a test for this, what would I do? I would call transfer from, and I would transfer from the holder. I guess I want to be, sorry, not the sender. I'm going to call the person who actually holds the tokens the holder. So I would transfer from the holder to the recipient the given amount. And then I would write my assertion, right? So I would like to assert that the balance of the holder after we call transfer is whatever it was before, reduced by the amount, and the balance of the holder, of the recipient is the balance of the recipient before minus the amount. Right? Now, of course, I've invented these new words I'm talking about, balance of holder after and balance of holder before. If I'm writing a test, I would just make variables, and that's exactly what I'm going to do here. So I have a uint, and before I call transfer, I'm going to save the balance of the holder and the recipient. And I do that by calling balance of holder and recipient. Right, so I'm recording the balances before. Then I'm going to call transfer from. And then I'm going to, record the balances after. Here, I'm just going to, so record the balance of the holder after and the balance of the recipient after. And now these two assertions make sense, right? I'm asserting that the balance of the holder after I called transfer from is whatever it was before, reduced by the amount, and the recipient, their balance should actually increase by the amount. Okay, so this rule looks a lot like a unit test or like a fuzzing specification. Now, I still haven't quite filled in all the details here. So the first thing is, I, again, came up with these variables, holder and recipient. And I need to declare my variables. But notice that I'm not going to give these any value. This is what the prover is going to do for us. It's going to try to search for values of holder, values of recipient, and I guess there's an amount here, so I need that as well. The prover is going to try to find values of holder, recipient, and amount that would violate either of these two assertions. Okay. Good. So we've written the spec. This is just about all we need for the spec. There's one additional thing that I just need to mention because I have to show it to you. When you call a solidity function, it's not just the variables that you pass in as arguments to the function that matter. There's also some state, right? There's the message sender and the block timestamp and a bunch of additional states about the blockchain that the function can take a look at. And in Certora, we have a type called an environment. We abbreviate env, and that holds all of these things. So this is like message sender, block timestamp, and so on, are all in this environment. And you have to pass that to when you call a contract function. Okay, so that's a little detail. Now we would also have to pass it here when we call balance of, but balance of doesn't actually depend on who calls it. It never even looks at the message sender or the block timestamp or anything else. So we have a shorthand here, something called a methods block. And you could just declare that there's this function balance of, which takes an address and it returns a uint. And there's this special keyword env free, which just tells the prover balance of is not supposed to look at the message sender or the block timestamp or any of that. And because we've done that, we don't have to pass an environment here. Okay, so a little bit of detail there. So that's all I have to do. I did not have to do any setting up. I didn't have to call a contract constructor to set up, the variables of the contract ahead of time. The prover is going to consider every possible value of all of the storage variables for the contract. So I don't need to do any setup ahead of time. I just have to describe the property I care about. Okay, so I'm going to go ahead and run this. Again, there's a nice IDE extension, but I don't know. I'm an old man. I like my terminal. I have pre-run a bunch of these. This will take about a minute to run. So let me get it started just to show you. So I need to tell it what contract I want and what spec I want. So I tell it to verify the ERC20 contract against the spec, which happens to be in Certora specs, ERC20 spec. Okay. All right. So what's going to happen when I run this command, or in the IDE I click a button? This is going to take the contracts and the specs, compile them, and then upload them to our cloud service. And you can see the list of jobs at prover.certora.com. And this is the run that I just posted. My earlier runs took about a minute, so this will probably also take about a minute. And we can wait for it, or I'll just go to the one that I pre-ran so we don't have to sit here for a minute waiting for it. But I do want to pause for a second and say, yeah, it takes a minute to run this, but the fact that it only takes a minute is kind of impressive. We're considering every amount, but also all of the storage state of that ERC20 contract. So there's an array of, a mapping of balances in there and a mapping of allowances. And the prover is going to consider every possible value for all of those balances and all of those allowances. And the reason it's able to do that is, as I was saying, as I showed with the sort of polynomial example, that it's actually trying to solve an equation that will tell it how to violate the assertion. So it's not trying random values or iterating over the values, it's just running them all. Okay, so I was filibustering a little bit. We now see that this run has executed, and we can take a look at the report. So first we see that env free func static check. that's checking that env property that I wrote, env free property I wrote down. Ignore that for now. The transfer from spec, this is the rule we wrote. And since I was filibustering, let's just show you. And we see actually that this property is violated. And we can expand and say, why was this property violated? And what we get from the prover is all of the information about the storage state of the contract and all of those variables in the rule, as well as a tree of like everything that happened when the rule is executing. So actually, let me just show you side by side here. Sorry, it's a little condensed. We'll do that. So here's my rule. We call balance of balance holder before equals balance of holder. That's this line, and then we do the next line, and then we call transfer from. Then we get the balance after and the recipient after, and we can expand this and see transfer from called, a different transfer from, which then called some other internal methods. So when you get a counterexample like this, you can really drill down and see everything that happened. But what I want to do just now is look at these variables over here. So we got a violation for one of these assertions, and we can take a look at what the variables were. So we were expecting the balance of the holder to go down and the balance of the recipient to go up. So we can see the balance of the holder after was 11, and the balance of the holder before was 8. The balance of the recipient after is also 11 and before was 8. That's a little weird. And the other thing we notice here is that this holder and this recipient actually have the same address. So we can pause and think, we got a counterexample here if the holder and the recipient happen to be the same person. So we can think for a second, what should actually happen if I try and transfer money to myself, right? I call transfer from, and I want to transfer from account X to account X. Well, actually, in that case, nothing should happen, right? If I try to transfer money to myself, at the end, my balance and everybody else's balance should be unchanged. So we can update our rule based on that insight, and we can say, actually, it depends. If the holder was actually the recipient, then one thing should happen. Otherwise, our two assertions should hold true. Okay, so if the holder and recipient are the same, well, what should happen is that the balance of the holder after should be the same as the balance of the holder before. Right? So if you try and transfer to yourself, nothing should change. But if you transfer to someone else, the holder's balance should go down and the recipient's balance should go up. Okay, so then we could rerun this. And instead of rerunning it and talking for another minute while it runs, I'm just going to go to my saved run here. This is the Certora portal. It lets you keep track of all of the jobs that you've run and gives you useful information about them and lets you search and so forth. Okay, so let's look at run 2. And I'm now gonna actually no, I'll so we still get a violation. So we fixed the rule. It should now correctly cover the situation if the holder and the recipient are the same, but we're still getting a violation. So again, we can expand this. We get a violation, balance must not change on a transfer to holder's account. That's a message I wrote when I was pre-running this. I didn't write it this time. And again, we get a counterexample. And again, we can look at the variables here. And let's take a look. So in this example, again, the holder and the receiver are the same. So that's interesting. And we can look, we were trying to transfer 4 tokens, and the holder before had 5 tokens, and after they have 9 tokens. So we tried to transfer, and the person who was the account that we were transferring from, their balance went up. And the balance of the receiver also went up, which makes sense because the holder and the receiver are the same. But that's not what should happen, right? If I call transfer from with my own address, my account shouldn't change. So we can then take a look at our contract. So I'm going to open the actual implementation here. And we can look. Let's just go look at the code and see if there's a bug. Okay, so transfer from does some checking. Oh, and then it calls this underscore transfer thing. So let's go look at that. This looks like the thing that actually does the transfer. So let's take a look at the code here. So the prover is telling us, hey, there's a bug in this code. And in fact, it's saying, hey, there's a bug in this code that happens when the sender and the recipient are the same. And in fact, we also know that the amount would be 4 and the sender's balance would be 5 and the recipient's balance would be 5 and so forth. But let's just take a look at this code, knowing that there's a bug that can happen if sender and recipient are the same. So what's going to happen? We're going to do some checking. All right, not going to be the 0 address. That's fine. We're going to call this before token transfer. Let's ignore that for now. Let's look at the actual meat of what we're doing here. So we record the sender's balance. That's going to be, in our example, the original sender's balance, which I think was 5. We're going to see the recipient's balance, also 5, because the sender and recipient are the same. Then we're going to do some checks, and then we're going to set the sender's balance to 5 minus 4, so it should be 1. And then we're going to set the recipient's balance to 5 plus 4, should be 9. But, aha, the sender and the recipient are the same. So this write here clobbers the thing we wrote before. And so we end up writing the final value of the recipient's balance as 9 instead of 1, which is, or actually, we should have subtracted and then added to the same number. So this is a bug. We found a bug in the code. How did we do it? We wrote down how we think the code should work. We ran the tool. The tool gave us a counterexample. We stepped through the counterexample. We said, aha, this is a mistake. Okay? That's how you use the prover. Let's fix this bug. So instead of taking the balance we recorded before, let's just take the current balance and add the amount. Okay, so we've just fixed the bug in our code, and then we can rerun the prover. And again, I'm not going to wait for it to run, but I'm going to go to my job list and find run 3 here. And when we rerun it at that point with the bug fixed, we now get a check mark. And that says, actually, no matter what value you have in storage, no matter what value you have for those variables, this assertion that you wrote is always going to be true. There's nothing interesting to show here because we don't have an actual bug that we've found. So the call trace is empty, the variables are empty because there's no example that actually violates the assertion. Okay. Cool. Now, you may actually say, wait a second, something's wrong here. Something seems a little fishy. Because the rule I've written here says, no matter what, if you call transfer from, afterwards, the balance of the recipient is going to go up. Well, that's not actually true, right? If the holder doesn't have any tokens, then it better not be the case that the recipient's balance goes up. And yet this rule still passes. The reason for that is that Certora by default ignores all the reverting paths. So in the case where the holder doesn't have enough funds, this transfer from is going to revert. Reverting executions don't change anything about the state, so they're usually not interesting. We do have a way that you can call and still pay attention to reverting paths. I won't show you that for this demo, but it's just good to know that for these rules, unless you say otherwise, the reverting paths are ignored. Okay. All right. So now I want to expand out. That's my first example. We found and fixed a bug. I want to expand this a little bit because we've only talked about how transfer from affects the balances. There's another piece of the transfer from mechanism, which is allowances, right? So if we go back to the interface, go back to look at transfer from. This just says using the allowance mechanism. Yeah. So the allowance mechanism, if we look at allowance, says you should only be able to spend however many tokens you've been given an allowance for. Okay. So that's something we can add to our spec for transfer from. We can assert that If you successfully spent the tokens, then you were allowed to spend them. So let's modify the rule a little bit just to take allowances into account. We could write a second rule. I'm going to just keep the same rule. There's a sort of stylistic question as to whether you break it up into many rules or keep it as one. But for this example, I'm just going to keep it as one. Okay. So we're still going to call transfer from. The thing I want to check at the end here is if we were successful, then it better be the case that the allowance that the holder gave to the recipient was in fact greater than or equal to the amount. Right? So in other words, if transfer from succeeds, the allowance should have been high enough. Okay. And in fact, if we look at the allowance, it notes that the value of the allowance should change when transfer from is called, and that makes sense, right? If I actually spend your money, my allowance should go down. I shouldn't be able to respend it. And so we can also include that in the spec for transfer from. Here I'm going to do, we care about the allowance before here, so I'm going to do allowance of the spender before, and the allowance of the spender after should be the allowance of the spender before minus whatever they actually spent. Okay. And of course, in order for this to make sense, I need to actually record those variables. So let's do that. Holder spender. Okay. So now I've updated my rule. I'm recording the allowance before and after the transfer from, and I am checking that if we were successful, the spender before making the transfer had enough allowance to actually make the transfer, and that their allowance is reduced. Okay. Now there's one more piece here that I have to account for, which is I'm now talking about this new third party, the spender. Who is the spender? Well, it's the person who calls the transfer from method, right? So if I call transfer from and say, transfer from Alice to Bob, I'm the spender, Alice is the holder, Bob is the recipient. Okay. And in particular, the sender is this message.sender variable. And so I'm going to add a new variable here, sender. And I only care about executions where the environment's message sender is actually that sender variable. So I'm going to add a require statement here. Leave the comment. I'm going to require that the message sender is in fact equal to my sender variable. Okay. So that ensures that whoever calls transfer from has to be this sender, and that means I'm recording the right allowances before and after, and then I can assert that they change. Okay, so now I've updated my rule. It now not only keeps track of how balances can change when you call transfer from, it also keeps track of how allowances change when you call transfer from. Okay, and we can rerun this rule. I did. There's not much interesting to see because the rule actually passes, so that's good. That means that transfer from implementation in our contract does actually treat the allowances properly. Okay. Now, I want to think from a higher level. If I'm a user of this contract, I now have some confidence. I'm confident that if somebody calls transfer from and uses it to transfer my tokens, they had an allowance to do so. Okay. But maybe I'm not totally comfortable because I would like to say that I gave them that allowance, right? This wouldn't put my mind at ease if some third party could come and give an allowance for me, for somebody else to spend my money. I wouldn't like that. So I'm going to write a second rule that sort of comes from that perspective of I want to make sure that I control my own allowance. So I'm going to call it only holder can increase allowance. That's what I care about as a user. Okay. All right, so how's this going to work? Well, if we wanted to increase the allowance, we'd have to call the approve method, right? That's when the value changes according to the comment. So let's call approve. And we need a spender and an amount. And somebody's calling approve, so we need an environment as well. Okay, and the assertion I care about is I want to say something like if so I'm the holder. If the holder's allowance, I'll just use allowance. If the allowance that the holder gives the spender increases, then it should be the case that the sender must be the holder. All right, so let me say that again. The thing I care about is if the allowance goes up, then the person who sent the approve message must have been the holder, the person giving that allowance. Okay. This on the previous line. And so we can write this as an if-then statement. And Certora, the CVL, has a special syntax for if-then statements like this. If allowance after is greater than allowance before, then, so this arrow is an if-then. If the thing on the left, then the thing on the right, then it better be the case that the message sender was the holder. Okay. That's the idea behind this rule. Now, now I need to sort of fill in my variables. So I need the allowance before, and I need the allowance after. Right. And again, I need this environment, so I'll declare that. And I need to declare these variables holder and spender and amount, so I'll do that. Okay, so and this is my rule now. I get the allowance before, call the approve method, get the allowance after. If the allowance went up, it better be the case that the person who sent the message was the person holding the funds. Okay, and we can go ahead and run this rule. I can show you the report, but it passes. This rule passes, and that means our ERC20 contract approve will only increase somebody's balance allowance if the sender was the holder. So that's great. That gives us some confidence that the approve method works correctly, right? That somebody else can't approve my funds. Except, you know, this doesn't really tell me that I have control over my allowances. This just tells me that I'm the only one who can call the approve method to change my allowances. And maybe that's enough because, hey, the comment says the value changes only when approve or transfer from are called, and we checked transfer from, and we've checked approve, and so we should be good. But of course, if you trust that the contract implementation actually follows its specification, then you don't need to do any testing at all, right? The whole point here is that the contract might have a bug. It might have a bug that actually means that the value can change not when approve or transfer from are called, but some other method. So what we'd like to do is not just call with an arbitrary holder and an arbitrary spender and an arbitrary amount. We actually want to call an arbitrary function, right? It shouldn't just be approve. I shouldn't just care that if approve increases my allowance, then it was me. What I really care about is if my allowance goes up after any method, then I should be the one calling it. So let's go ahead and do that. Just like you can declare variables, and Certora will try all possible values, you could declare a variable of the special type method, and Certora will try all the possible methods. Okay, so instead of calling specifically approve, we're going to declare a method f and call it with this environment. Now, arbitrary methods can take arbitrary arguments, and so we can add the special type call data arg, which stands for an arbitrary number of arbitrary arguments, and we can pass that args into f. Okay, so read this as call any method in the contract, give it any arguments, and run it with any message sender. Okay, so we've updated our rule now. We record the allowance, do anything, get the allowance after. If the allowance went up, it better have been me, the holder, that actually called the function. Okay. So we can run this rule, and let me show you the report for that. Going back to the job list, this is run 6 here. Okay, so we see actually, this this rule we just wrote actually fails, and we can expand it. And because we called an arbitrary method, the prover will try it on every single method, and we see that most of them do actually satisfy that property. But there's this weird, interesting. There's this weird method in there called pull the rug, and somehow this pull the rug method is allowing somebody to increase their allowance. That's maybe a bad sign. So let's take a look at our source code. Oh yeah, there's a pull the rug function right in there that somebody put. Maybe they put it in there after we already did our audit and our testing. But if we had a specification like this in CI, it would catch this weird bug, which allows anyone's allowance to suddenly be given to this weird address, dead beef. And if we switch back over to the prover and look at our example, we do indeed see that the new spender who has the increased allowance is this bad address, dead beef. So because we were able to think at a high level, what would I care about? I'd care about if my allowance went up. The Certora Prover was able to let us check that property on all methods, and we were able to find, weird things that we never even thought of, didn't even know were in the contract, that shouldn't be there in our bugs. So that's the demo. I don't want to stop share. I just want to switch back to my slides. So that's what I have for my demo. I showed you a little bit of what the prover can check. There's a whole bunch of things. Once you start thinking at a high level, what are all the possible things my contract can do? There's a lot of kinds of properties you can write down. So an important one that I didn't show you are contract invariants. So for example, if you have a liquidity pool, a constant product formula might be an invariant, or even just the total supply is equal to the sum of the balances. That would be an invariant. We saw a method specification, we saw a transfer from, but any method that you have, you can write down a specification for. Solvency is a good example of a kind of property. It's an example of an invariant. The contract should always have enough assets to cover its debts. If there's a pool draining exploit that lets somebody take all the funds out of the contract, then unless it also lets them take all the debts out of the contract, a solvency rule like this will catch it. You can check things like permissions, front running, really almost any kind of property you can describe in English. You can write a rule that will check. We have a demo site, and I think we're also going to provide some keys. Yeah, that's what I have. Thank you very much.